Hey Global Impact students, Mr. Ellinger here. This lesson is on solving systems using tables and graphs. Our learning target for the lesson is we want to be able to solve a linear system of equations using a table or a graph. Some essential understanding for the lesson. A system of equations is solved by finding a set of values that replace the variables in the equations and make each equation true. A point of intersection, xy, of the graphs of the functions f and g is a solution of the system y equals f of x and y equals g of x. Linear systems can be analyzed using the nature of the solutions. The possibilities are one solution, infinitely many solutions, and no solutions. So to solve a system of equations, we need to find a set of values that replace the variables in the equations and make each equation true. A linear system consists of linear equations. A solution of a system is a set of values for the variables that make all the equations true. You can solve a system of equations graphically or by using tables. So here you have an example. What is the solution of the system negative 3x plus 2y equals 8 and x plus 2y equals negative 8? So here we have two equations that we're working with simultaneously, and that's called a system. So the first method is to graph the equations. And you can see here to the right, our red line is the graph of negative 3x plus 2y equals 8, and the blue line is the graph of x plus 2y equals negative 8. The point of intersection appears to be negative 4, negative 2, but we can check by substituting the values into both equations. So if we plug negative 4 in for x and negative 2 in for y into both of our equations, we find that both equations are true, so negative 4, negative 2 is the solution of the system. The second method that we have is we can make a table. Write the equations in slope-intercept form. So here we transform negative 3x plus 2y equals 8 into y equals mx plus b form. Same thing here. X plus 2y equals negative 8 into y equals mx plus b form. And then we can do this on our calculator, actually, and I'm going to show you how to do this here in just a minute. But if we were to make a table by hand, we can start making a table of values. And as you can see in the screenshot over here to the right, when we find the same y value in both equations, the x value that goes with it is the solution to the system, the x value, the solution. And then the y values that are the same are the y values that are the solution. So when x equals negative 4 in both of our two equations, y sub 1 and y sub 2, we get a value of negative 2. So negative 4, negative 2 is the solution to the system. All right, so some questions that we should just consider. The first one, going back to method 1, why should you check the intersection point you read from the graph by trying the values in both equations? Well, if you think about that, anytime we solve something, we should always check our solutions if we can. So it's just a check to see, did we graph our lines correctly? Because we could graph two lines. If we graph one of them incorrectly, we can still find the intersection point. But if we don't graph the lines correctly, then that intersection is not going to be the solution to the system. So we should always go back and check our work. It's not too terribly complicated to do so we should always try that. All right, and another question down here in method 2, why do we want to put the equation in slope-intercept form? So why do we want to do this? Well, if we are using our calculators, it's easier to put these functions in. And when we're trying to plug in x values and solve for y values that go with those x values, y equals mx plus b form or slope-intercept form is just an easier form to work with. All right, so let's try one of these. So why don't you go ahead and pause the video right now and go ahead and solve the system by graphing. And then I'll show you how to do this on the calculator. Okay, so there are my two graphs, and as you can see, the way that I graph these two is they're both in standard form, so I just found the x and the y intercepts on both. I didn't use the slope, but I didn't use a straight edge to draw these. I just wanted to graph them, get a visual representation of the situation. But as you can see, based on the graph that I've drawn right now, I could be led to believe that negative 1, 3 is a solution to the system. But the problem is that's not the solution. Okay, it should be fairly obvious. If I plug negative 1, 3 into both equations, in the first equation I get a statement that's false. Now that point does work in the second equation, but not the first equation. So that's not the solution to the system. Now it's going to be clear that I'm not very far off. The solution is probably going to be somewhere in here or maybe back in here if I draw these lines appropriately with a straight edge. But what we need to do is we need to either use a straight edge if we're doing this on paper, or if we have some tools that we're using like on Math Excel or whatever, it's much easier because the lines that are drawn are automatically straight. But let's talk about how we do this on the calculator. Okay, so from the calculator we saw that the solution to the system is -2,4. And back to the graph that I drew by hand, how could I clean this up so that I could see that? Well, one little trick that we could do, let me do my red line again, and instead let me have this in slope-intercept form. Alright, so y equals -1/2 x plus 3. What I can do here is I'm just going to put some points on here using my slope. And what I'm hoping happens, I don't even need to draw the line really, I'm hoping that I get a point that coincides with a point from my second equation, which is y equals -x plus 2. So let me put some points here. So here we have y-intercept of 2, down 1/1 for a slope of -1. And I could work back the other direction. And here, when I get here, I do have a point that coincides with a point from the other line. So this point right here is my solution, and as you can see, the coordinates of that point are -2,4. So really, you can do this just by plotting points and not graphing the line. Okay, so this works great for integer solutions, but when we have any type of decimal or fraction answers, we're not going to be able to probably use this technique. So that's where the graphing calculator comes in handy, and other techniques that we'll take a look at. Okay, so let's take a look at an application problem here. The table shows the populations of the New York City and Los Angeles metropolitan regions from the census reports for 1950 through 2000. Assuming these linear trends continue, when will the populations of these regions be equal? And what will that population be? So here's our data from the U.S. Census Bureau in the table here. And what we know is we know population data for the two cities. What we need is the point in time when their populations will be the same. That's what we're asked. And our plan, what we're going to do is we're going to use a calculator to find linear regression models. We're going to plot the models and we're going to find the point of intersection. Okay. To do this by hand, first of all, we don't even have an equation, and these are probably not a perfect linear situation. So we need to use some technology here. Do this by hand would be a very, very tedious task. So suggestion here is to enter all the numbers as millions, rounded to the nearest 100,000. For example, our first population data there for New York City, we're going to treat 12,911,994 as 12.9. Okay, so 12.9 million is what we're gonna go with when we do this. So I'm going to show you guys how to. We already know how to enter data into a list on our calculators. We already know how to generate a scatter plot, but now we've got two sets of data here. So we're going to talk about how to enter both those lists, generate a scatter plot to show both, do a regression on both, and plot that regression model, and then find that intersection. So let's take a look at how we do that on the TI Inspire. Okay, so let's talk about how we do a regression on our calculator, linear regression, and we're going to take it a step further. We're actually going to graph the regression equation, and then we're going to find the intersection of the two regression equations that the calculator generates for us to solve our system. So we know that we enter our data into a table. Once we have our data entered, then we can have the calculator perform the regression for us. So here I'm in that screen, and what I'm doing is I'm telling my X list, I've got my year since 1950, and my Y list is New York City. And what you'll see here is it's telling me it's going to save my regression equation that it's going to generate for me into F1, function 1. And that's what we want. We've got to pay special attention to that. So, and it might even be beneficial to make a note of that our New York City equation is going to be F1. So you can see here in my table, it's done that for me. So now what I want to do is I also want to generate the regression model for LA. So let's go ahead and do that. Menu, statistics,
See, when I'm in the table, remember, when I'm in the table format and I've entered data in, the menu button is going to pull up my statistics options and the other options that I have. Slightly different than when I'm on a graph. So my X list are my years since 1950. My Y list now is LA. And you can see that this regression equation is going to be stored in F2. And you can see here, I have both regression models. My regression model for New York City, my M is going to be 1.46571. That's the slope of my line. My y-intercept is going to be 12.8857. And conversely here with the LA, the data from the LA population growth, we have a slope of 2.5 and we have an intercept of 3.80. So let's just talk about what that means real quick. The y-intercepts tell us, since we're in 1950, it kind of tells us the starting point in 1950. So this 12.8857 is like for our model, is the y-intercept. That's the starting population in 1950, 12.8857 million people. In LA, it's 3.80476 based on our model. Now, that's not exactly what our table says. Slightly different because this is the model for our data. But our M values, our slope for New York City is 1.46571, and for LA is 2.51143. So what that means is the slope is greater for LA. And so remember, a slope is a rate of change. So the population of LA is growing faster than the population of New York City from 1950 to 2000. And just to verify here, our R values, 0.96 is a very good R value, and 0.98 is a very good R value again. All right, so we want the calculator to insert a graph page for us. So here we have our first, member up here, our little tabs are the pages that we have in our document. We only have one page right now, so this is 1.1. So what we can do is we have a couple different options. We can click the document button, which will give us the document menu, or you can go within the document itself, click this arrow here, and that will give you the document menu as well. But we want the calculator to insert a page for us, and we want it to be a graph page. So you can see now we have two pages open. We have a 1.1, which is our table, our data, and 1.2 is our graph. So what we want to do is we want to go ahead and have the calculator generate the scatter plot for us. So let's go to graph edit entry, and we're going to go to a scatter plot. And now what it's asking us is it's asking us, what do you want to use for the X values and what do you want to use for the Y values? So if you remember our X values, if we go back to our table, in this box here, we called them years since 1950. So let's go ahead and put that in here. So we have years since 1950, and we have NYC. So once we enter the variables into their appropriate, or assign the data from our table into the appropriate variables, what we want to do is press enter, and we saw that nothing happened. So what that means is we just need to set the window, the viewing window of our graph. You can see right here our X values are from -10 to 10, our Y values are from -6.67 to +6.67. So we don't see any data yet. We can change the viewing window. Okay, so if we go to menu, we have this window zoom function. And you can see once I bring that window up, I have all different kinds of options. I can set the window myself. I can zoom in on a certain part of the graph using a box, just a standard zoom in or out. You can do some standard zooming, quadrant 1 zooming, lots of different options here. But when we're working with data, we want to go ahead and do a zoom data. And as soon as you do that, you see that our data is displayed. And I'll just move this out of the way a little bit. This is just showing me that the blue graph is years since 1950. So there's my data for New York City. Now let's do the exact same thing for LA. So let's go here, scatter plots. We have years since 1950 for our X, and we're going to put LA in for our Y. And when we do that, we get, there's our red dots. Now we don't see those because if you remember, our data from LA, these values are greater than the LA values, so we don't see them. So remember what we can do. Let's do a window, zoom, and our data there. We get both scatter plots here. So I'll just move this out of the way a little bit. And now you can see here are our data for LA, and here are our data for New York. Now, we want to see our regression models that the calculator generated for us. So let's go back to menu, and we want it to graph edit or entry, we want it to functions. Okay, when I pulled up the function menu, it saw, or what we see is we see an F3 of X. So the 3 is like, this is the third function that the calculator's entering. So there's already been 2 functions entered, but we don't see them. So this is asking us to graph a new function. Well, we don't want to graph a new function because the calculator already created the 2 regression functions for us. These are already stored into the calculator as F1 and F2, and the way that we access those is we use our arrow button up, and there's F1, okay? So as soon as we get that function up, we just want to press enter and it graphs it for us. So there is the regression model for New York City. And let's do the same thing for LA. Again, when I go to a function, edit a function, or enter a function, it gives me the new function. I don't want a new function, I want to use F2. So there I get F2 up. As soon as I get F2 up, I go ahead and put that on there. And you can see there's the regression model, the line of best fit, but we now call that the regression model for our data for New York City. So we can't see the intersection point. It's going to be somewhere off our screen to the right. So let's go ahead and adjust our window. Now if I press zoom data doesn't work here because the data is the scatter plot, okay, or the 2 scatter plots. So what I'm going to do is I'm going to do a zoom out. I need to zoom out and see more of this graph. So I'm going to put the center of the zoom towards the upper right hand part of the screen so it zooms out in that vicinity. Okay, wherever I put that magnifying glass, it's going to use that as the center of the zoom. So we can now see we've got our intersection point. So when you have this magnifying glass, it will continue to be on there. And when you want to get rid of that magnifying glass, just remember to hit your escape button. Your escape button is always how you get out of a function or whatever it is that you're doing. So now we can see we have our intersection up here somewhere. And some of these things that are popping up here, I can move my graph, I can slide it, I can rotate it. I can do lots of different things. I can move these labels out of the way. So if I wanted to move this function name over here, and I wanted to move this function name over here, just click and drag. But now remember, we want our intersection. So our intersection is found in the menu, analyze the graph. Okay, lots of different options here that we're going to use as we move forward. So here we're just using an intersection. And again, our lower bound somewhere to the left of the intersection. And this doesn't have to be right next to the intersection. Just drop it wherever you want to out to the left. Drop it wherever you want out to the right. And click, and there it gives you the intersection point. So we get an x value of 8.68 and a y value of 25.6. So we'll need to discuss the context of that in our problem. But that's how we do it on the calculator. The data suggests that the populations of the New York City and Los Angeles metropolitan regions will each be about 25.6 million in the year 2037. Now, a question to follow up on that: how accurate do you think the approximation is for the population? Based on the technique that we did and what we used, it's probably, all the math that we did is fine. But one thing when we start to study populations, and we hit on this a tiny bit in Algebra 1, but we'll hit on this a lot more in Algebra 2, is populations usually do not grow in a linear fashion. They grow in an exponential fashion. So we used a linear model here to come up with a model for the data, but as we're going to find out soon, we don't want to use linear models for population growth, so we want to use exponential models for population growth. So just give you a little preview of what's to come. Okay, so we can classify a system of 2 linear equations by the number of solutions. We can have what's called a consistent system, which has at least one solution, and we can have an inconsistent system, which has no solution.
A consistent system can be broken up into one of two types. We can have an independent system. An independent system has one solution, and a dependent system has infinitely many solutions. So we can have an independent consistent system, and we can have a dependent consistent system, or our system can be what's called inconsistent if it has no solutions. So the graphs for an inconsistent system are always parallel lines. They're not going to intersect, which kind of makes sense. If two lines don't intersect in terms of a system, then we know there's not going to be a solution. So there's no solutions. In a dependent system, the two equations represent the same line. So when we have infinitely many solutions, the two equations in the system represent the same line. And most of the time when we have this dependent system, the system itself, when it's presented to us, the two equations are not going to look the same. But if we transform them both into slope-intercept form, that's when we can see that we do in fact have the same equation, which will generate the same line. And then obviously the third choice is where our lines are going to intersect and we have a solution, and that's called the consistent independent system. All right, so how do the slopes of parallel lines compare? Just to review a little bit, parallel lines we know have equal slope. Okay, so here in our parallel line graph, the red line and the blue line both have the same slope. They differ by a y-intercept. So they have the same slope, different y-intercept. How do the slopes of coinciding lines compare? Well, here are coinciding lines, meaning the same line, meaning one line right on top of the other. Obviously, those lines are also going to have the same slope if they're the same line, but they will also have the same y-intercept. Same slope, same y-intercept are coinciding lines. So how can you tell whether the graphs of two linear equations with the same slope will be coinciding lines or parallel lines? Just check the y-intercepts. If the y-intercepts are the same, we're going to have coinciding lines. If the y-intercepts are different with equal slopes, then we know we're going to have parallel lines. Okay, so without graphing, is the system independent, dependent, or inconsistent? So we have our two equations, 4y minus 2x equals 6, and we have 8y equals 4x minus 12. And again, another use of our slope-intercept form. Let's go ahead and take both of these into slope-intercept form. So my first equation, 4y. So the graphs for an inconsistent system are always parallel lines. They're not going to intersect, which kind of makes sense. If two lines don't intersect in terms of a system, then we know there's not going to be a solution. So there's no solutions. In a dependent system, the two equations represent the same line. So when we have infinitely many solutions, the two equations in the system represent the same line. And most of the time when we have this dependent system, the system itself, when it's presented to us, the two equations are not going to look the same. But if we transform them both into slope-intercept form, that's when we can see that we do in fact have the same equation, which will generate the same line. And then obviously the third choice is where our lines are going to intersect and we have a solution, and that's called the consistent independent system. So here we have a visual graphical representation of each one, and you can see those there. All right, so how do the slopes of parallel lines compare? Just to review a little bit, parallel lines we know have equal slope. Okay, so here in our parallel line graph, the red line and the blue line both have the same slope. They differ by a y-intercept. So they have the same slope, different y-intercept. How do the slopes of coinciding lines compare? Well, here are coinciding lines, meaning the same line, meaning one line right on top of the other. Obviously, those lines are also going to have the same slope if they're the same line, but they will also have the same y-intercept. Same slope, same y-intercept are coinciding lines. So how can you tell whether the graphs of two linear equations with the same slope will be coinciding lines or parallel lines? Just check the y-intercepts. If the y-intercepts are the same, we're going to have coinciding lines. If the y-intercepts are different with equal slopes, then we know we're going to have parallel lines. Okay, so without graphing, is the system independent, dependent, or inconsistent? So we have our two equations, 4y minus 2x equals 6, and we have 8y equals 4x minus 12. And again, another use of our slope-intercept form. Let's go ahead and take both of these into slope-intercept form. So my first equation, 4y minus 2x equals 6. There's my first equation, y equals 1/2 x plus 3/2. And my second equation, okay, so here you can see we have two lines that have same slope, two equations, same slope, but the y-intercepts are different. So what does that mean? Well, if two lines or two equations have the same slope, but their y-intercepts are different, then we know right away that this tells us that we have parallel lines. And if we have parallel lines, then that means there is no solution to our system, okay? But if we have to classify the system, what does that mean? Well, we classify that as what's called an inconsistent system. Okay? No solution means an inconsistent system. And, you know, these classifications, independent, dependent, inconsistent, we're not going to get too crazy with those. You know, it's nice to know what they're called. But right now, the critical thing is to know, one, how to solve a system by graphing, finding the intersection of the two lines. And then obviously knowing whether there is a solution or not, or whether there are infinitely many solutions. So that's it for now. Hope you guys have a great day.